nice to see everybody virtually. As Brian said, I'm a professor at the University of Oregon, the Center for Optical, Molecular, and Quantum Science. This talk today is a tutorial. It's so-called introductory, but what that means is people that have a good, solid physics undergraduate background in quantum theory. So it's not meant to be a totally general to the public talk, which I've given many of those before. This is a somewhat more advanced talk, but still assuming that people are not experts in quantum optics or quantum information. Okay, so there's two audiences here. I think we're being joined by two audiences. One is students in the Applied Physics Masters in quantum and nanotechnology at the University of Oregon. And the other group is from the ASPEN-Net. And I'll say what that is. And these programs are funded by the National Science Foundation. So Brian, do you still see my cursor? It disappeared.
It's gone.
It's gone. Let's try that again. Why would that disappear? Let's try it again. Now it's good?
Yep.
Okay, I'll just leave it like that. Okay, let's get moving then here. So first of all, I want to point out that the ASPEN-Net is a part of it's a testbed of the National Quantum Virtual Lab, the NQVL, which is a NSF-funded program whose goal is to cement the U.S. as a leader in quantum technology. And the national program is consisting of about 5 to 10 different testbed demonstration projects, including the ASPEN-Net. And the goals of this program are listed here: to share infrastructure across the country, you have had to be a user-driven approach, have a phase of development through the different projects, and the projects include these types of topics here. And finally, workforce development is an important part of it. And you can learn more about ASPEN-Net at this website here, quantum-aspen.net. Okay, now to talk about the two test beds that are currently in operation within NQVL that have to do with quantum networking. The first one is our program, ASPEN-Net. It's 3 different sites: CU Boulder, University of Oregon, and UIUC, led by Brian Smith. And this scheme is based on single photon path entanglement. Good thing about this is it requires, the benefit is that it has a high rate of entanglement distribution compared to other methods, but it does require path phase stabilization, which I'll say a little more about later. The other program is led by Stony Brook University. It's called SkyNet, and it's based on 2-photon qubit entanglement. It does not require path phase stabilization, and its benefit is that it does not require path phase stabilization. So there's pros and cons of these two approaches, and in the future quantum networks, these types of approaches will be merged into one large application scheme. If you'd like to see more details about the ASPEN-Net scheme, you can see a talk here by Mike Mazurek, which is posted on our YouTube channel. Okay, and this lecture that we're recording right now will also be available on the ASPEN-Net YouTube channel. Okay, so with that, I'm going to back way up, and I'm going to tell a story, not about ASPEN-Net or SkyNet in particular, but about quantum networking in general, and then also give some quantum theory to give you a little more deep background for those who like theory. And then I'm going to talk about some applications. And this talk will be quite broad. It won't be focused just on ASPEN-Net, which you've seen at other talks. So I'm going to talk about the setting, the stage, the characters, and the action, and the payoff. So first, I'll talk about paradigm shifts in the concept of information more generally. Then I'll talk about quantum networking. Then I'll talk about the physical layer, or the hardware that makes this possible. Then I'll talk about some of the action of this story: how to create single photon and know it's created, how to load a state into a quantum memory, how to entangle a pair of memories, how to create a network of entangled memories. And then finally, once we have that, we'll talk about some of the applications. So there's a lot to cover, and I'll go pretty fast. If you have questions, please type them into the chat window, and Krista Shalm, my partner in this lecture, will be answering questions by typing the answers. And then if he has a question for me that it goes beyond what he can type, he can interrupt me and ask me to answer the question. Okay, so please do enter a lot of questions that Krister can interact with. Okay, let's first talk about history of the paradigm shifts in the concept of information. I'm starting way, way back. In the year 1387 was the first recorded, at least in the English language, of the word information. And it was written that 5 books came down from heaven for the information of mankind. Okay, I'm not exactly sure what the context of that is, but this was the idea that information could be beneficial to humankind. Well, in 1948, Claude Shannon established information as a measurable quantity applicable to communication theory. So this was a paradigm shift in the way humans thought about information. It's a resource or a quantity that can be quantified mathematically. And then later, physicist Brouwan wrote that entropy measures the missing information on a physical system. That is not its randomness. So entropy has to do with information. And then physicist Peirce wrote that in communication theory, information is associated with uncertainty and the resolution of uncertainty. And the most interesting relation between physics and information theory in those days was thought to be in the evaluation of the unavoidable limitations imposed by the laws of physics on our ability to communicate. You see, so in those days, people thought of quantum mechanics as a limit because the uncertainty principle prevents you from controlling things at a microscopic classical level. And so it introduces what they thought of as errors or noise. Well, this paradigm was then sort of augmented by the idea that quantum physics is related to information. Heisenberg wrote that this continuous change in the quantum state takes place with the act of registration. That means measurement, because it is the discontinuous change of our knowledge in the instant of measurement that has its image in the discontinuous change of the state. So he's saying that the state is not a physical property of an object. A state is a description of an object, which can change when you make a measurement. Schrodinger wrote about entanglement, that the best possible knowledge of a whole does not include the best possible knowledge of its parts. That's a very mysterious statement, but we now understand precisely what that means in the context of quantum entanglement. Well, then there's another paradigm shift that happened after this, the idea that information is physical and also information is quantum. So the idea that it was used in the 1960s to study the physics and the engineering of computation and computer memories, and then also developed in great detail by people like Shapiro and Sretanovich and Hellstrom. It's using quantum theory in a very deep way to calculate information channel capacities. Okay, then 1970, finally, Charlie Bennett invented the term quantum information theory. And this is a screenshot of a photograph of his lab book from 1970, where he wrote down for the very first time quantum information theory, and he attributes this to a conversation with Steve Wiesner. Okay, so he's pointing out now that arbitrary superpositions of quantum states is actually the stuff transmitted or processed by a quantum system, and that's not classical information. Okay, then on we go to the Bell inequalities experiments. Correlations are stronger than possible in classical physics, which plays a large role in everything we do now. Quantum key distribution, quantum teleportation, and all these fantastic capabilities came about by realizing that quantum theory is not just a limitation on what you can do, it actually offers new things that you can do that you couldn't have done if the world were strictly classical. Okay. Now, another paradigm shift that really happened in the 80s when Feynman and Seth Lloyd started talking about quantum simulation. In other words, Feynman said that you can simulate one quantum system efficiently if you have a machine that encodes the other system that's to be simulated in the quantum states of your simulating system, because it's a natural fit, really. And then finally, David Deutsch and Grover and Shor and Steen push forward the idea that not only could you do simulation, but you could actually do universal quantum computing in theory. So this really broke open the dam, leading to all the current excitement about quantum information theory and technology, which we call the quantum revolution 2.0, which is a phrase coined maybe by Dowling and Milburn, in which QIST is quantum information science and technology. We have sensing, communication, simulation, and computation, which are these three pillars here. In quantum computing and simulation, we have all these fantastic approaches and applications. In quantum sensing, we have these applications and approaches. And in quantum communication, we have some of these, which I'll discuss in more detail later. But the point we like to make is that quantum networks, when we get them built and operational, they will enable and link together all the different diverse quantum technologies. Just as the internet does now, it links together all information processing systems. So let's move onward then. Okay, what is quantum networking? This sets the stage for what we'll talk about later. Okay, well, first of all, what is quantum information? You can define it as information encoded in quantum states of physical objects. That's it. It's information encoded in quantum states. Such information cannot be encoded and sent as classical bits, for example, through the internet. You cannot write down a quantum bit or a qubit on a piece of paper. You have to write it into a physical object like a spin or a single photon. Okay, now a quantum network is a network of channels and nodes that transfers or shares quantum information. So that means you have to send quantum states from one place to another, and you cannot do that by writing them on a piece of paper and mailing that piece of paper. Okay, so a very important aspect of a quantum network is what's called quantum interconnects. And here's a little diagram that we included in a review paper that we wrote a few years ago, like a roadmap stating what kind of interconnects are needed to support a quantum network. And on the far right here, I have a quantum computer, which can be a modular computer, which can have different modules connected by these red arrows, which are quantum interconnects, which transfer quantum states between the modules and also between a memory. And these little wiggly things are photons. The photon, say a red photon, goes into this device called a quantum frequency converter. It can convert that red photon to a green photon and put into a green quantum memory, or it can convert the red photon into a infrared photon, which has no color, so I drew that as black. And that can go into a quantum repeater called, which I'll talk about later, and it can bounce around inside of this quantum network through quantum switches and eventually go to users, can go to quantum sensors, or quantum sensors can send sensor information from the sensor back into the network, which could then be transferred over to the quantum module, quantum computer, et cetera, et cetera. Now, the resource or the commodity of all this operation is quantum entanglement, which is what Schrodinger talked about first. And the idea is that entanglement means that you have a quantum state of two different objects, A and B, but that state cannot be written as simply a product between the two. It's a sum of products. Now, what that means physically is that measurements on one of these objects, say B, will turn out to be correlated to observations on object A. So it simply means they're not statistically independent. It means they're correlated and statistically dependent. But it turns out that in the quantum world, this concept of correlation can be very different than the concept of correlation is in the classical world. Okay, now, I'm telling us stories, but let me give you the spoiler. At the end of this story, we'll see that the quantum network is constructed using quantum repeater chains. So now let's try to get to that final result there. Okay. Hey, well, let's say a little bit more about that. The number of links needed to connect two nodes A to H and the time needed to establish end-to-end entanglement increases exponentially with distance. There's many reasons for that, but in part it's because quantum operations are typically probabilistic. They only work with a certain non-zero probability. So the more different tries or trials that you make, the longer it takes, and it turns out to be exponentially bad. So this was thought to be a major a hurdle in building entanglement links over large distances. But very smart physicists figured out that you can overcome this by using a quantum repeater chain. And if you do this correctly, it gives you only polynomial overhead in the number of links and the time needed to establish entanglement, as opposed to exponentially bad overhead. Okay, so the way it works, and I'll say much more about this later, you break up the long length into a bunch of shorter lengths, and then you try to do entanglement locally between these closer by links indicated by these dotted lines. And eventually it's probabilistic, but the solid line means that A and B have succeeded in making entanglement. The other ones failed, okay? So you keep trying this until all of the links have succeeded. And then you have to do what's called purification, which I won't talk about in detail, but it means you have to have actually many qubits shared between each of these nodes, not just one pair of qubits, but you have many qubits entangled and shared. And then you do some operations called purification, where you can improve the quality of the entanglement while decreasing the number of entangled qubits. But in the end, all you need to have is one good pair of entangled qubits between any two nodes. So that's how that works. And then after that is all set up, these nodes will now do a local, because they're nearby, B and C are close to each other, or even inside the same laboratory. They'll do an operation that does entanglement swapping, which kills the entanglement between these inner nodes, but now establishes entanglement between A and D over the longer path. And they keep doing that, and they keep doing that until, boom, you finally have entanglement across a very large distance. And this was proposed by these authors in 1998, but has never been implemented on a large scale. Okay, that was the spoiler. Now let's go back into detail and look at the characters that are going to play the role of the physical layer. That's atoms and photons. Okay. Well, there's two kind of qubits. The first type is called stationary qubits, which are represented by matter, by atoms, molecules, electrons, and so on. And that's useful for storing quantum information. So you can have, for example, atomic electron in spin. The spin can spin clockwise or counterclockwise, which can represent a zero logical or a one logical. Or you could have states of a superconducting circuit, and you can think of this in a cartoon manner as the current is flowing around clockwise in a loop or is flowing around counterclockwise in a loop to represent the zeros and ones. Well, the other kind of important qubit is called the flying qubit, and it's useful for transmitting quantum information. So that's the photon. Okay. Now, photon, you can encode information in the following ways. One is polarization. If the polarization of the electric field oscillates in the horizontal direction like this, compared to the propagation direction, which is the arrow, that's a H or a zero. If the electric field oscillates vertically compared to this propagation, that's called a one, vertical. Or alternatively, you can encode information in the time of arrival, called time bend states. So a photon could arrive early or it can arrive late. This can be a single photon, but it's in a superposition of late wave packet and an early wave packet. And each of those can represent a 0, 1. Or you could encode quantum information in the color or the frequency of the photon. Like a red photon could be 0, a blue could be 1, but you can have a single photon which is in a quantum superposition state of red and blue. Okay, or you can encode the information in the path. You could have two waveguides here, and the photon could be in a superposition, or it could be in one or the other, or the upper waveguide or the lower waveguide. So those are the different encoding schemes that we're most familiar with. Well, photons have good, bad, and ugly. The good is that they're very fast, they have high bandwidth, they're robust in optical fiber, they're easy to manipulate, they provide interconnects between various atomic systems, and they can achieve a room temperature operation. You don't have to cool them down. The bad is that the states are the photons are embedded in a continuum of frequencies and locations. The photons are easily lost. Photons are non-interacting, so logical operations are hard to accomplish. And finally, photonic systems are very hard to scale up because of these bad properties. It's hard to scale up to billions or even thousands of photons. So we typically tend to think in terms of handfuls of photons, 5 to 20 photons doing some operations. Okay, now let's get into a little more mathematical description of these quantum states. Okay, what is a photon? It's an excitation of the quantum electromagnetic field. We call it a particle, but it's really not a particle. It's really an excitation of a field. Okay, so here's, for example, a single photon state of two modes. So modes could be, for example, horizontal and vertical, as I've written down here. Here's an example. You could have a state that's some coefficient alpha multiplying this state, which is the H mode is occupied and the V mode is empty. But that can be in superposition with another coefficient in a phase. The H mode is empty and the V mode is occupied. Well, that's a complicated way to write it out. So we like to abbreviate that in what I call photon speak. We pretend that the photon is a particle and it is in the state alpha H plus beta V. Okay, so that's just a code language for this actual state of the field. And we know this is true because fields can contain more than one photon. And when you have more than one photon, this idea of photon speak language, it becomes very complicated, but it's still very easy to represent everything in terms of the state of the field. Like, does this mode have 1 or 5 photons in it? That's an easy way to talk about it. So photon is the name of a state of the field. That's how we usually look at it. Okay, let's talk about more mathematics, and then we'll get rid of the mathematics and go back to the qualitative discussions. So first of all, photons are sent as pulses. A CW laser puts out a continuous beam of photons, but the photons are not controlled in their emission or arrival time. So instead, we use pulse lasers, which make short wave packets of light. And just like a laser pulse can contain more than one photon, we can also create pulses of light that contain exactly one photon, which I'll tell you how to do that. Now, these wave packet modes are what I call discrete. They're not a continuum if you prepare them correctly. So here's an example of 3 discrete wave packets that you could make. In the time domain, you have these 3 different wave packet shapes. They're actually orthogonal in the sense of if you multiply one by the other one and integrate in time, you get 0. They have a spectral shape like this. This is just a Fourier transform relation between the two. So that's what I mean by wave packet modes. But of course, I can also change the color of these wave packets. I can translate them in time or in position. I can do many things with these wave packets. Now, I call these modes because mode is actually a classical concept. It's a simple solution of the Maxwell equations for the field. There's nothing really quantum mechanical about the mode until you populate that mode with a quantum state. Okay. So here's an example of 3 distinct time bin modes, and I can animate them and make them move along. You see, they remain essentially orthogonal or non-overlapping as time goes by, and that's just a Fourier transform of some Gaussian wave packet. Okay, now we're going to get into deep mathematics, but only for 3 or 4 minutes. So bear with me if you don't like equations. Here's Maxwell's equations. Here's a frequency representation. We can express the electric field E of t as a function of, instead of time, as frequency with a carrier e to the I minus omega t. If we think about monochromatic mode expansion, we can expand the spatial aspect of this monochromatic field in terms of spatial modes. The spatial modes I denote as U. They're a function of R, position, They could be standing waves, traveling waves, ring cavity modes, whatever. And the sigma is a mode label. So we have to sum over the sigma mode label, and E is a scale factor, and A for that mode is the complex amplitude of that mode. Okay. They're orthogonal in
Brian,
space.
sorry,
Yeah.
Mike,
Yeah.
there's a question in the comments that I think um, maybe it would be good for you to address. So there's a question that says, why is it bad that photon states are embedded in continuum of states?
Okay. Thank you, Christopher, and for that question. It's bad because it makes them hard to control. You see, like take an electron. Electron is ideal in the sense that it has exactly two states. When it's up, it's definitely up. When it's down, it's down. Those are eigenstates, and they're discrete. There's only two of them. But in a photon, like I said, if we go back to here, see, I could translate this wave packet by a whole unit over to here. That'd be a discrete transformation. But I could also translate it only by a small amount. I can translate, there's an infinite number of different amounts by which I could translate it between these two states. So that's what I mean by continuum. There's also a continuum of colors, infinite number of colors between a red and a blue. And so they're not discrete. And quantum mechanics is usually easier to control the states of objects when everything is discrete and not continuous. So it's really a matter of being able to control it and also then to be able to measure it. So that's the best I can say for that. But this is exactly why I'm talking about the wave packet modes, because they are discrete if you control them in the proper way. And a lot of the research we do is in learning how to control the wave packets so they are discrete, they're well enough described as discrete so we can actually use them as qubits. Because we want two state systems, not a system that has an infinite number of possible states. Okay. For a waveguide, we have these two waveguides, call it sigma equals 1 and 2. That's the mode label, and they have different locations. And W here is a function of X and Y. That's X and Y, the transverse variable. And so if I just specify different W functions, I can specify different locations in this guided structure here, different wave packets. And there's a longitudinal function, e to the I k z. Okay. And then we can, if we just look at one of these guided waveguides, we can now do the trick I mentioned before about creating these temporal wave packet modes. So first, let's drop the sigma label and just talk about A of omega. That's the amplitude at a given frequency. But as I said, a wave packet mode is actually a continuous superposition, so integral over d omega with A of omega, and then the longitudinal mode is fixed, and depending on the function we choose for A of omega, we can create different wave packet modes, one of which I've drawn in this little picture here, and it propagates according to this equation in the plus z direction, which is along this way. Okay. Now, furthermore, we can mathematically re-express this A of omega function. This is all still classical physics. We can express that as a discrete sum of Fourier functions, which I call f sub j of omega. This is analogous to Fourier transforms, where you can represent a continuous function as a sum of sines and cosines, which have discrete frequency separations or discrete wavelength separations. So that's another example of making a continuous description into a discrete description. So here we have these capital AJ, which are the coefficients. So the original function, A of omega, is a continuous, but our new function, A sub j, is a function of discrete labels. J is an integer. So now it's the capital AJs that describe our state, because the f of omega functions are given, or they're selected by you. This is called generalized Fourier series. So when we do that, the entire electric field, E of R and T, now is expressed this way. It's in terms of the AJ, which are these coefficients, times these functions in the box, which are the wave packet modes. Because if you specify an f of omega and put that into this transform, you also have the e to the ikz, which makes a wave packet. And the time e to the minus omega t makes the whole wave packet propagate. So now we've boiled the whole problem down into a set of well-known wave packet modes multiplied by to be determined coefficients, capital A, J. All right. Now that picture allows us to quantize the field in a very convenient way. We just showed that we can write this electric field as a continuous integral over omega, but we can also rewrite it in terms of these wave packet modes, AJ. Okay, so that just summarizes what we did before, but now these little hats on the variables indicate these are quantum operators. So E hat is a field lowering operator. It lowers the number of photons. If I multiply this operator on a state, it decreases the number of photons. Okay, and so does the capital AJ. But capital AJ decreases the number of photons only in the wave packet mode defined by F sub J. Okay, so then we have a scaling factor here. Thus, we can write this electric field operator as a discrete sum of these wave packet modes, each having a lowering operator, capital AJ. Now we've converted this continuous description into a discrete description. And now all we have to do to quantize the whole system is notice that these capital AJ operators obey this boson commutation relation. So A is the annihilation operator and A dagger is the creation operator. And that's really all there is to it, the mathematics. Now, just what does it mean? It's interesting what it means, actually. Remember, if you know basic quantum mechanics, you know that N is the number state for a harmonic oscillator. That's fine. That's still true. Now, harmonic oscillator in our case is corresponding to a single frequency. But these are wave packet modes. They don't have a single frequency. They're a continuous sum over or integral over frequencies. So N is the number of excitations in mode J. That's still true. So N is the number of photons in mode J. Okay. Now that's interesting though, because I just told you that mode J does not have a well-defined frequency. So how can both of those statements be true? The answer is that N does not correspond to the energy of a field mode. If you take a field mode to be a wave packet mode, then energy is not equal to N h bar omega. Simply isn't, because the different frequencies are smeared out. So here's a test question for you. See if you followed all that. Given a wave packet mode UJ, the single photon state is A dagger acting on a vacuum, which is simply this state here. Now I take that state, it's a non-monochromatic single photon wave packet, I shoot it through a prism, and according to Pink Floyd, the light is spread out across a spectrum, and now I have an array of detectors. And what happens? Think about that for 10 seconds.
Sorry, can you be more precise what we want to know for what happens? You're asking what's the mathematical description of the state, or you're asking what is the actual question you're trying to get an answer to?
The actual question is, you're an experimentalist and you're at the detector here, and you have an array of detectors, and I'm asking you what happens at this array of detectors. Thank you, mysterious Paul Kwiat. The answer is only one detector pixel will click, because even though there's many different frequencies and possible energies contained in this wave packet, there's only one photon. So you can say that a single photon simply represents the fact that one detector will click, or that one atom will absorb something. So it's the discreteness of events that is represented by this single photon, not the discreteness of energy. Okay, moving right along. Given that, we're going to get rid of all the mathematics and go back to qualitative descriptions. The action of our play here will be how to create a single photon, how to load a state into a quantum memory, how to entangle a pair of memories, and how to extend the number of entangled nodes. Well, how to create a single photon? Since we just heard a question from Professor Paul Kwiat, I should acknowledge that he was one of the pioneers in this area. And by now it's considered a standard workhorse in the field. It's called pulse spontaneous parametric down conversion, SPDC. And for those who don't know this, the idea is you take a blue laser pulse which could be quite short, could be picoseconds roughly, or nanoseconds. You send it into a nonlinear optical crystal of certain type, and typically, with a probability of 10 to the minus 9, one of the blue photons will be split into a pair of red photons. We call the idler and the signal photon. Okay, and it represented by this picture here on the energy diagram, the omega p pump blue photon has twice the energy and twice the frequency as any red photon. But notice that the red photons can be emitted in different combinations: long, short, medium, medium, short, long. We call those frequencies omega, omega prime. But you see, this gives us a very strong time and frequency correlation, because if one photon is long, the other one is short. So in terms of the spectrum, the joint spectrum, you can see this nice little picture here. This is the frequency of the signal photon and the frequency of the idler photon. And you can see there's a correlation, anti-correlation. If the signal frequency is high here, then you trace over here and you see a low idler frequency. But if the signal frequency is low over here, you trace over here, you see a high idler frequency. So this represents correlation. Well, I said earlier that correlation in quantum mechanics means entanglement, and that's exactly right. We can write the quantum state of this two photon system as this wave function, psi of omega, omega tilde, and these two creation operators for these two acting on the vacuum. And this function here, psi squared, is the joint probability to detect one photon at omega and the other photon at omega tilde. Now, this is very beautiful, but it's also bad because this means it's a multimode quantum state. So if I measure one of the photons frequency, I don't really know much about the quantum state of the other photon. It's kind of a mixed picture. But let me skip quickly and just say that you can make this picture much more beautiful. You can make it circular. And what this actually means is that there's no entanglement in terms of the frequencies. And this, in many cases, this is what you want. Even though I said earlier that entanglement is a good thing, sometimes it's a bad thing. And the reason it's good here is because if I measure the signal photon at any frequency, then it tells me that the idler photon is left over in a pure quantum state, because I've got now this function here is a product of f times g. It means the quantum states are now a product of the signal photon state times the state of the idler, so they're statistically independent. So if I measure one of them, I get a pure state in the other one. That's the beauty of this scheme here. Okay, now, given that, we're going to use that technique to produce a single photon in a pure known quantum state. We do this trick over here. We detect one of the photons, which is called a herald, and then what that does is it heralds or conditions or leaves the other photon in a nice pure state. So in this case, we're producing a certain polarization of this photon, but then just using wave plates and quarter wave plates, I can, of course, convert that into any state that I want. And for example, I can create now by this setup, whenever this herald detector gives a signal, which we call a click, it's producing this other photon, alpha H plus beta V. And I can control the parameters alpha and beta using these half wave plates and quarter wave plates. Okay, so that's how you create a single photon and you know you have it. But it's probabilistic. It doesn't happen every time. You might arrange it so it happens 1 out of 10 times. Now, what are we going to do with that? Okay. Over here, I give a shout out to the Center for Quantum Networks, which I'm also affiliated with, another NSF center program, and it's called the Engineering Research Center. And within this center, we're developing this kind of hardware. And we wrote some papers here analyzing this problem, and we came up with an improved scheme for the following memory loading scheme. So here's the scheme that we proposed. This is based on a scheme called Dwan and Kimball. And it's based on the following. You have an atom, and you want to transfer this quantum state of the single photon, which is alpha and beta, into this atom. Well, atom has two ground states, G1 and G2. So the goal in the end is to have the atom in the state alpha G1 plus beta G2, where this alpha and beta are exactly the same as what came in on the photon. Now, this complicated apparatus does the following. There's a ring cavity. The atom's inside the ring cavity. the ring cavity is tuned to have its optical frequency resonant halfway between an atomic excited state E and halfway between these two ground states. Okay, omega 0 is the photon, I think, and omega C is the cavity. And the two ground states are separated by capital delta. So what you can see is classically, if you send light into a transition in a two-level system above resonance, you get a certain phase shift. But if you send it in below resonance, you get opposite phase shift. So these two resonances, depending on which of these levels is populated, will impart a different phase shift to the photon. Now, it's convenient to put the atom in a cavity so that when the photon goes around this ring cavity and it comes out down this other path here, it has experienced a phase shift. And the phase shift corresponds to which of these atomic ground states the atom was in. But now here's the trick. Before the photon comes in, you use a microwave pulse to prepare the atom in a superposition of ground states, G1 plus G2. So now this poor photon, when it comes out of this cavity, it doesn't know if it got a plus phase shift or a minus phase shift. That is, it's in a quantum superposition state of having both or either phase shift. Now you take that piece of the photon and you interfere it on this beam splitter with its other half. So it's not that I have two photons, but it's not like you have one half and a better half. It's like you have one photon, you split it on a beam splitter by polarization. The alpha H part of the photon goes into the cavity and gets a phase shift or no phase shift. The V part of the photon gets diverted to this lower path and does not experience any phase shift except what you put into it with this little device here. Now, when those two halves of the photon meet up again at this beam splitter, they interfere. And it turns out that depending on the phase shift that the photon experienced in the cavity, the whole photon is reunited with itself and arrives at D plus or D minus. And this shows a cartoon of the phase shifts that you can get, positive or negative. And you adjust it so the difference of the two phase shifts are plus pi over 2 and minus pi over 2. The difference of those is pi. Okay, so therefore, if here, yeah, so I have to move quickly here. If there's a click at D plus here, it projects the atom into this state, alpha G1 plus beta G2. If there's a click at D minus here, it projects the atom into the state alpha G1 minus beta G2. So in both cases, you know exactly what state you've produced in the atom, and they're equivalent to this initial state of the photon. The photon, of course, has been destroyed. It's no longer present, and that's consistent with the no cloning theorem, which says you cannot take a single quantum object like a photon and copy it into another object without first destroying the first one. So we've done that. Okay, end of that story. That was a single photon loading of a memory. But now we go to the other topic, which is the two photon scheme. Remember I said earlier that quantum networks can be based on single photon path entanglement, or they can be based on two photon entanglement. And in this case, we have two photons. We're keeping both of them. We're not going to use one as a herald. We're going to keep them both. And we produce them by some clever arrangement, which actually Paul Couillot invented, to make HV plus or minus VH. Okay, so if this photon is measured as H, we know the other one is V and vice versa. Okay, so that's our state. Now we're going to use two of these Dwan-Kimball memories, and we're going to send the photon to each one, and we're going to detect at A plus or A minus and detect at B plus or B minus. And we have the same scheme, plus or minus pi over 2. And now when we get clicks at the outer detectors, we get the following. If we get a click combined at A plus and B minus, so A plus and B minus, that projects these two atoms into this entangled state, G1, G2 minus G2, G1. So isn't that beautiful? And it works in theory, it works with very high fidelity, and it works with very high probability. You can get the probability and the fidelity greater than 0.99. Okay, and there are people trying to set up experiments to implement this kind of a entanglement distribution. Okay, I know I'm going fast, but let's keep going. The next thing we can do is we can extend this entanglement scheme to a chain. I said earlier that entanglement chains are important. So here's one that I came up with recently. This is unpublished work, actually. So we first do this over, yes?
Can I ask a question? This is actually a question for me. So for this scheme, for just a
Yes.
single case, how do double pairs? So instead of emitting one pair at a time, if you emit two pairs, how does that affect things in the scaling for this? Does it introduce like in terms of errors?
Yes, it doesn't introduce errors, and therefore you have to operate the photon flux at a low flux. So you minimize the rate of producing these photon pairs, so you don't get double pairs. Because if you have double pair coming in, it can fool you and think you have some result when you actually had a different result. So you have to lower the rate, which is a bad thing, right? You want to have a high rate. So we've worked in great detail with theorists at MIT, like Jeff Shapiro, to work out what is the optimum scheme. And there are ways to overcome this problem. And that's by using essentially many photon sources. So if you have 20 sources, each one operating with low probability, and you can combine all those together into a single optical fiber, that's equivalent to having one source with a higher rate, but you've now suppressed the double pair problem. So we have papers published on how to optimize that. And it looks actually very promising if you can implement that. Thank you, Krister. So let's assuming that we just have one pair, ideally, and then I'm going to go on and explain this building up of a chain. So we have two of these systems working in parallel. And when they finally announce that they have entanglement locally between this pair and between A and B is their entanglement, and between C and D, then they reconfigure and they now do the same operation between B and C. And once B and C are successfully producing the right click pattern between their detector pairs, I did a little bit of analysis. It's actually very simple. Then it goes like this. I won't prove the math, but then what you do is you do a readout between of B and C. So you send a laser into the B atom between level G and level E, and you run it very hard, and you look for photons to come spitting out. If they come spitting out, that means you've conditioned the B atom into its ground state G1. You do the same thing on the C. And if both of them are now indicating that atom B and atom C are found to be in the ground state G1, then you've actually produced entanglement between, wasn't sure if I got it. You actually now produce entanglement between A and D. Here's the final result. So you now have this entanglement between A and D. Oh, here it is. This blue equation at the far right. You now have G1A, G2D minus G2A, G1D. So you've managed to extend the entanglement between the A and the D nodes, and they can be far apart. So in principle, although this has not been implemented, in principle, you could concatenate or chain this up and get a longer chain of entanglement and create entanglement between the nodes. You could do this operation that I showed you before, where each of these nodes was a Dwan-Kimball memory. And in principle, those operations can be very high efficiency and high probability and high fidelity. Okay. So now we ask the question, well, in a real network, we don't want a linear chain, right? We all know that the internet has a linked, a two-dimensional linked geometry between different locations. There's not just one path between Chicago and Boulder. There are many possible paths. Okay, so in this cartoon picture, which was created by the Center for Quantum Networks in this paper by Pant et al., they did the following calculation. You start with a whole bunch of nodes. Each node is a blue circle, and each node has 4 quantum memories sitting in it locally. Could be on a single optical table. Now, each node, like this one, or say Alice at this node, works in parallel to create entanglement between all 4 of her neighbors. And every other node is doing the same thing. And Bob is over here trying to create entanglement between those using some kind of scheme, local scheme. Well, I shouldn't say local, I should say short distance scheme, maybe 10 kilometers. So they don't need quantum repeaters between these nodes. They just need optical fibers. Now, there's a probability P that on any given trial, entanglement will be successful between adjacent nodes, okay? And that's the parameter that this paper studied in great detail. Then what happens is you wait and wait until percolation theory tells you that if you wait long enough, you will eventually create some path of entanglement between Alice and Bob. And it turns out it's a percolation problem, so there's a threshold. Once you pass a certain number of trials, given the p-value, you're almost certain to have some path between Alice and Bob. And in this particular example, I show there's two paths that happen to be created between Alice and Bob, between these chains here. So Alice has entanglement between her memory 1 and Bob's memory 3, but Alice also has entanglement between her memory 2 and Bob's 4. These other ones are irrelevant. They didn't do anything. Okay, so that's pretty cool. And you can calculate the probability and the scaling and how this all depends on the fidelity, the probabilities, the losses, and all these different imperfections that might occur in a real network. So this is part of modeling the overall architecture of a quantum internet. And it goes way beyond just thinking about quantum optics of single atoms and photons. Okay, but this theory is all well understood, and people are trying to build these kind of systems. So now we're finally to the last part, which is how can we use such a network to implement some interesting applications, which is the payoff. Okay, here's 9 possible applications. I'm going to talk about these 5: device-independent quantum key distribution, distributed quantum computing, short and long distance, quantum cryptography, random number generation, distributed sensing, etc. There's also timekeeping, physics tests, communications, etc. There's a lot of different things that one could do if you had a working quantum network. Okay, so the first one is entanglement-based quantum key distribution. And I'm only going to show this one slide. I'm not going to go through the details of how it actually works, just tell you the good news that in 1991, Eckert proved theoretically that if you could produce very good quality polarization entanglement between a photon going to Bob and a photon going to Alice, you could use it to create secret keys. And there's been a lot of theoretical and experimental work in this direction over the past 30 years. In fact, Nobel Prizes have been given for this kind of work. So I drew a cartoon here pretending that Bob and Alice now have a stored entanglement between two of their memories. Then what Bob does, Bob sends, he creates a photon from his memory and goes into an analyzer. An analyzer is a polarization analyzer made of a calcite crystal, which can be rotated to one of two possible angles, 22.5 degrees or 67.5 degrees. And then following it, the photon is deflected into one or the other detector. And that's the discreteness of quantum measurement. So it kind of projects, or it collapses the state onto one state or the other, depending on the rotation angle and depending on the amplitudes of the entangled state, which are given here. The state is HV minus VH, simple linear combination. Now, Alice takes her quantum memory, generates a photon, and sends it through another calcite crystal, which has two different possible settings, 0 degrees or 45 degrees. And for those who know things about the so-called Bell inequalities, so-called Bell test, those are very familiar numbers. It turns out that as people, for example, Christopher Shalm, who is our moderator here, did an experiment, showing that there's no way to describe the correlations that are observed between Alice and Bob using classical probability theory. Only quantum theory, as far as we know, can describe these probabilities. And there's something called loophole-free Bell test, which means just what I said, that you can do the experiment so carefully. For example, the nodes are so far apart that and everything happens so quickly that there's no time for the two sides to conspire by sending messages back and forth at the speed of light, because the measurements are over with before any messages could arrive both at Alice and Bob, from Alice to Bob, or from Bob to Alice. And it turns out that if you now can violate the Bell inequalities, which is the condition for proving that it's quantum, or rather proving that it's not classical, if you can violate that in a very good way, then you can prove that it's so-called device independent. That means it doesn't matter what the hardware apparatus in the middle is. It doesn't matter what the measurement is. Nothing matters except if Alice and Bob can actually verify later that their correlations could not be described by classical theory, then you know you have entanglement on the assumption that quantum mechanics is valid in the universe. And to our knowledge, it is. So that's very cool because it really takes away a lot of hacker capabilities. Doesn't matter what the hackers or the eavesdroppers do in here. If Alice and Bob still are receiving good amounts of entanglement, they know they have a quantum secure signal. And Myers and Yao have proved that you can use this entanglement data that Alice and Bob collect to create a shared key. So now Alice and Bob have a shared key of just classical numbers. They both, in all the trials, they get 0, 0, 1, 1, et cetera, et cetera. And again, there's a lot of entanglement purification and error correction that has to be done, but I won't give you the details of that. But in the end, Alice and Bob end up with the secure shared key, which they can then use to communicate across the classical insecure internet, because a shared key of random ones and zeros is perfectly 100% secure. Okay, so that's a very cool thing. Now, look at this poster that I just got in the mail the other day. This is the CU Physics Department wall calendar for the year 2026. And our poster children here are Palfrey Kaveri and Christopher Shalm. Christopher, of course, is our moderator today. And they're being celebrated here by the University of Colorado for having built a random number generator using pretty much the same hardware that I described on the previous page. Okay, so this really does produce true random numbers, and you should be aware that a classical digital computer cannot generate random numbers because it's running on an algorithm. But in quantum mechanics, there's no algorithm that the universe uses to generate the probabilistic outcomes of quantum measurements. As far as we know, there's no algorithm, and you can prove that because you have the violation of the Bell inequalities. If the universe was using an algorithm that was local to Alice and Bob to produce random numbers, then you could not violate the Bell inequalities. So this is a very cool application. All right. Changing to now quantum state teleportation. Another very important application of quantum entanglement. So here's my cartoon. Professor Xavier has a state that he has engineered called alpha H plus beta V. Now, this state could be a particular state. Now, alpha could be, 2/3, and B could be the square root of 1 minus 2/3 squared. There could be a phase number in there. So that's a particular quantum state, and it's a photon, say, and he wants to transfer that state over to Bob. Now, there's two ways to do that. One, he could simply send the photon over to Bob. Okay, but remember, there's a problem is that you can't send a photon 20,000 kilometers to Bob, because most likely Bob will not receive that photon. It'll be lost somewhere. So you need a more robust way to transfer that state without actually transferring that particular photon. So it's called teleportation. So it starts from stored entanglement, you see, which we've built up using our quantum repeater chain. And Bob and Alice have now stored quantum entanglement. And for example, HAV Bob minus VA HB. And this entanglement is now used as a resource for state teleportation. So how does that work? Okay. Alice takes a photon from her memory, sends it into what's called a joint measurement. And the professor sends his photon into the joint measurement, and they're measured jointly to produce an outcome. Now, this measurement tells something about the entanglement between A and X, but it does not tell the state of A, and it does not tell the state of X, but it still gives you some particular outcome. There's typically 4 possible outcomes in such a measurement because there's 4 possible combinations of states. But remember, because it's all quantum superposition, when Alice makes a measurement, gets 1 of 4 outcomes, it does not tell her the state of X. That's important. But now she takes that information, she tells Bob with a classical message, which by the way, travels less than the speed of light, over to Bob. And she tells Bob which of the 4 possible outcomes she observed. So that tells Bob something about the entanglement between X and A, but doesn't tell Bob what the state X really is. So now Bob takes his photon, he puts it through a known state transformation based on the information he gained from Alice. And based on that known state transformation, this B photon is converted exactly into the state X. Now, Bob doesn't know what that state is because he hasn't measured it. He just applied this, known transformation. But nevertheless, this photon is now exactly in the same state that the professor's photon was initially. And Professor Xavier's photon has been destroyed consistently with the no cloning theorem. So that's very cool. And the point is that the entanglement in these memory nodes can be built up over time and stored using that protocol that I showed you earlier. So once Alice and Bob have this, then they can immediately move to do this teleportation trick and transfer the professor's state over to Bob without having to worry about probabilistic errors and all kind of things like that. So that's very cool. Now, you can use quantum state teleportation in modular quantum computers. And I won't describe this beautiful experiment in detail. It's rather complicated, but it was done by the group of John Wei Pan in China a couple of years ago. And it just shows that you can have a cloud of cold atoms over here on the left and another cloud of cold atoms over here on the right. And you can prepare the cloud of cold atoms in a certain quantum state using this little protocol here called write, which I won't describe. And you can make a measurement. This would be like Alice. She makes a measurement, and then if she gets yes, she tells her apparatus to now make another measurement and read it out. At the same time, she tells this other location here, it could be a very long distance away, say 150 meters of fiber, tells this location to start doing some operations. And then, if they do the operations correctly, they get a photon that comes out. These 2 photons go into the joint measurement. That was that joint measurement that I mentioned. So this is like X. This is the professor creating the state of his system. Alice is making a side measurement. They do a joint measurement, and then the information is transferred over to Bob. Bob can do a transformation. And now his atomic cloud is now left in the quantum state that was initially prepared in this initial atomic cloud on the left. So that's teleportation. And now the point is that these 2 atomic clouds can be used for quantum computation in some way. It's very complicated, but there are many experiments where people are using atoms as quantum qubits. This can also be done with trapped ions, which is another. It can also be done with superconducting qubits. So teleportation can be used to communicate between quantum computers or within a modular quantum computer. In other words, this could be a single lab, and you could have many different atomic clouds operating within different vacuum chambers in one lab. You could have 20 vacuum chambers, and the atoms in each of the different vacuum chambers could be communicating with each other through this quantum teleportation links. All right, very cool. Now, another example I'm going to show very briefly is work that we've been doing here at Oregon, based on work that was done by Michelson 100 years ago. It's called Extending the Baseline of Interferometric Telescopy using distributed quantum entanglement. So what Michelson did was he has some distant object like the Betelgeuse star. It sends down very weak signals. And if one photon comes from the object and goes into these 2 telescopes, which could be separated by a few meters, then if that light interferes, it can go and hit this detector or that detector. Okay. And it turns out then by changing the phase here, you can put a little phase plate in here and vary the phase, and you can see the signal go back and forth between the 2. That's called an interference pattern. The signal depends on the phase. And it turns out that by making these kind of measurements, you can gain a lot of information, for example, about the diameter of the star, not just the location, but the actual diameter. And that's what he did. Okay, now it turns out that if you can separate these 2 telescopes by a larger distance, you can obtain information about diameters of stars that are much farther away, because the angular, separation of those 2 objects would be much smaller. So to resolve those, you need to have a larger so-called baseline separation. And we have a project in collaboration with Oregon and the folks at UIUC, Paul Kwiat and others to try to implement schemes like this. Well, you can see what's going to happen here. The problem is, as you make these two telescopes farther and farther apart, it's more and more difficult to do what Michelson did, which was to combine the two paths, because the photon is going to be lost. Let me just emphasize, there's only one photon that's emitted by the star, but that one photon goes in both paths, and eventually it's recombined with its other half and makes interference. And only one of these detectors clicks. It's not a two photon experiment, it's a one photon experiment. Okay. So how can we leverage this idea of one photon? Well, we can now use our earlier ideas where you have a single photon source, which I showed earlier how you build that using Heralded's SPDC. You send that single photon into a beam splitter. You send half of it over to this telescope. You send the other half of the single photon to this other telescope, and you interfere those halves with the halves of the photon coming down from the star. So there's only two photons, one from the star and one from the source. And so if things work out probabilistically well, then you'll get one click at this receiver side and one click at this receiver side. And by doing that, it tells you information about the phase. So as you modulate the phase over here of this path, which only contains one half of a split photon, you modulate this phase, it imprints itself onto the path entangled state of these two paths. This one photon path entangled state is now imprinted by this phase. And as you modulate that phase here, you can modulate the clicks, coincidences between these two sides. And by looking at the interference pattern of this modulated click interference, you can determine information about the diameter of the distant star. So we're trying to implement such a system in reality. Now, using path entanglement, the rates can be high because only one photon needs to be distributed. The other way to do it would be to have two photons from the star and two photons from the ground and interfere them. But now you have four photons. So you have a much higher chance of losing photons. So by using single photon sources, you can win. However, remember I said at the very beginning, that's the benefit of single photon encoding. But the downside is you actually need to have a phase stable network covering this entire baseline. In the meantime, we just blundered ahead and we built a small telescope on the top of our physics building over the past year. Matt Brown and Francesca Sansevini. I've been working with Brian and myself to build this telescope, and we have optical fibers coming down from our little observatory. This is a very small one. It's only 8 feet tall. And the fibers go down to our lab, and we can collect the photons from stars and send them to our lab. But as I said, to make this really work, you need a repeater chain that transfers this single photon split into two paths into quantum memories on the two distant sides. You need a repeater chain. And then the idea is you would load up these quantum memories with many single half photons, which are entangled according to this formula here. And then when you're all ready, when these memories are loaded, you can then send out a burst of photons. Because remember, the star is emitting photons all the time, right? But the problem is you have atmospheric turbulence. And the atmosphere changes significantly, on a time scale less than 1 second. And that will mess up your phases. So the idea is that if you can store up a bunch of half photons and then send them out in a burst, say only covering a few microseconds, then you can, in that short time period, you can get around the atmospheric turbulence. So this is a possible way, which is very, I would say, futuristic and forward-looking, which may take at least 10 years to implement. But that's what we're working towards, long distance performance.
Hey,
so,
Mike, I have just a quick question.
Yeah.
Instead of doing what you end up with here, which is equal frequency, different time band modes, which I agree would work, no question, but you need the memories. Couldn't you just have very closely spaced frequencies that are different and then just do a bunch in one burst, just do a bunch of spectral things that are close to each other? Because you kind of have a white light interferometer anyway, I guess. So
yes.
It seems like you could deal with different colors simultaneously.
Yes, absolutely. You could do that. And that's the multiplexing scheme, which I mentioned earlier in the context of Dwan Kimball memories. You can multiplex in many ways. And it turns out that in order to beat the direct Michelson technique, you have to use both time and frequency multiplexing. You really need to have something like 10,000 channels working within the time frequency window in which you can make observations. So this makes it extremely challenging, and I would say kind of like a LIGO scale project. It's not easy at all.
Yep. Okay. Yeah, that's what I thought. Okay, thanks.
Yep. Okay, and now the question is, can long distance optical networks actually be stabilized in their phase sufficiently well to implement schemes like that? Well, the answer is yes, but it's state of the art. And here we have a picture of Boulder with the beautiful flat irons behind it, and we have the campus. This is the Gilla building where I worked during my PhD work many years ago. And over here is the NIST campus, and there's a direct optical link through the sky here, but there's also an optical fiber link going through the city. And what they've shown is that using this optical fiber link, you can synchronize or you can phase stabilize two ion traps, aluminum and a ytterbium ion trap, using these optical reference cavities, these beautiful little things here. And you can stabilize that to a frequency of 18-digit accuracy, which is extremely good. But notice that this kind of measurement requires some amount of time, like maybe 1 second. Okay. You have to do signal averaging for some number of seconds in order to achieve this kind of accuracy between two clocks. Now, in our system, like I just said, we want to send out a burst of photons and make measurements between the two locations, say one telescope at NIST and one telescope at Gilla. And the problem is that over much shorter times than 1 second, the fibers can jitter and fluctuate. And you're not going to get 18 digits of accuracy if you just look at it for less than a microsecond. So there's still some serious work to be done to achieve 18 digits of accuracy over, say, 1 microsecond. But our collaborators at NIST think that this is definitely feasible. So with that, I will end. This is the beginning of a very long technological and scientific project. We think it's extremely interesting. This is our group here at the University of Oregon. As I mentioned, this lecture is in connection with the Applied Physics Masters in Quantum and Nanotechnology at Oregon. If you or anybody you know is interested in getting a master's degree in quantum, please contact Brian Smith here at the University of Oregon. It's also sponsored by the Center for Quantum Networks, which is the NSF Center studying different approaches to building quantum networks than is the ASPEN-Net Center, which is also the sponsor of this lecture. So with that, I will end and open it up